This is one of the circuits I'm pretty much gonna build. This is the simpler one, the one without the 2 transistors on it, but this is for my variable power supply. Don't forget to put a diode, reverse bias diode on the output so I can make a plus or minus supply with it. And I'm probably gonna, I haven't looked at this yet, but I'm gonna try to see if I can, I should be able to do that. Put a double gain potentiometer so that in here somehow, so that both of these could actually, act as a simultaneous supply. And I'm going to build a dual tracking supply, and I'm going to build another one too, but I'm still trying to figure out exactly how I'm going to do that. But, again, this requires a dual pot, and then leaving the regular pots in there so that you can use them for, like, individual adjustment, but you can put a switch in there that short circuits across the dual potentiometer if you want to take a given leg out of that circuit. So you can just make this the variable, but otherwise, if you're going to put it in dual mode, you should actually turn this resistor down to 0. Okay, and then you use the pot, the dual pot, to control both halves of the power supply. So you turn that down to 0 on both sides, but you can use these individually to do an offset off of the dual tracking feature. So that's probably how I'm going to do both. So you're talking about a potentiometer plus a little switch across it, which a toggle switch, which you can turn off and on. If you make it a double pole switch, you can make it so that you can actually switch both of them out at the same time if you want. Which I don't know. I'll have to think about that, because there may be times when you want to switch back and forth for some reason, individually. I don't know. Without changing your settings. You know what I mean? Although again, you could probably do that. Well, I mean, you couldn't though. I mean, because if I had a double pole switch or double throw DPD3. Double pole, single throw switch or whatever. Well, it's, a double throw single pole switch. So, I would. It always gets confusing, because okay, what's a pole? Well, a pole is a polarity, right? So, okay, that's something you should throw a switch into, right? So that should be one of the switch positions, so you can have like multiple poles like in a rotary switch. But then a throw should be the switch itself. So double throw means 2 separate switches. Double throw 4 pole, or double pole or 4 pole single throw is a single rotary switch with 4 positions. Anyway, I don't know, but it's easy to think of a throw, as being, again, a handle you grab to throw a switch, right? So it should be a throw. That would be a slang term for throw. But then again, it is possible to think of it in terms of a position you would throw a switch into. So, and a pole could just be some weird, okay, that's one polarity of the motor, and we got another pole over here with the other opposite polarity, so it acts to control the direction of the motor. So I mean, there's just different crazy ways you can look at it. That's why I always get confused. I don't think I'll ever get that remembered. But anyway, but yeah, so if you do that, I'd put an individual switch on both of them, just to give you maximum versatility. And then anyway, we can do that. But anyway, I'm trying to figure out how this damn thing works, so I'm going and trying to record my analysis here. Starting, so if you kick this, let's say we had a light bulb put on here as a load, right? She tries to explain it, but it's still not very clear. But see, she's putting a light bulb on there as a load, okay? So, if we have a light bulb, or whatever on here as a load, Okay, at first, you just turn the thing on. Well, this starts at 0 volts, so, and it's a 40 volt input, so, we got 40 volts here and 0 volts here, okay? So that means there's a 40 volt drop across this 3055 transistor, and this sense resistor here is for current sense. She was using this down to like 0.1 volt, 1 ohm in one of her videos, but again, that may make it harder to adjust the current, since it is a current sense resistor, so you may kind of change your output or whatever. But anyway, so this would have 40 volts across it, at first. Okay, well, it's an off transistor, so it can't flow through the transistor here. So it comes down here. This is also at 40 volts, and it sees a PNP transistor, but oh, hey, this transistor's off, so it can't supply current to this transistor to turn it on. So it looks at this 100K resistor, and again, everything right now is at 40 volts. And again, ignore this part of the circuit right now. Just assume everything here does not exist. So, again, we got this at 40 volts. Okay, and that's a diode drop. That's another diode drop. And this is at 0 volts. That's got no current flowing through it, so it's at 0 volts essentially here. So this is really at 1.4 volts above ground on this base. So that means we're dropping 40 minus 1.4 volts across this resistor. Okay, and if you do the math on it, it works out to be in the neighborhood of 400 microamps. So basically you end up getting 400 microamp current flowing through here pretty readily. Alright, now of course, let's assume this is a smaller transistor, probably has a beta of 100, so 400 microamps turns into 40 milliamps pretty easily, which is more than enough to allow 40 milliamps or so of current to flow through this base, multiplying that by another 100-fold. So it's 400 milliamps, and then up to 4 amps could be flowing through this. And that might indeed happen if it weren't for the chain of events of this like turning itself on as it goes through this process. But in theory, this could supply, and this is kind of a power transistor right here. This BD140 is. This is more of a standard TO92 package transistor, I believe. All the rest of these are. But at any rate, so you get a potential of up to 40 milliamps, okay, that could be flowing in there. But the point is certainly current can flow from here through here through here. This would be almost saturated, at first, because again, it's got the potential for a lot of current to flow through it. But the point is that yes, you can certainly get your supply current will begin to turn this transistor on here and allow real current to actually flow through it, which of course will start to develop a voltage across our sense resistor, but again, we won't worry about that at the moment. But anyway, if left to its own devices, basically this would just continue right up until this transistor was just dropping a very minimal voltage across it, taking into account these two diode drops. So it'd be like 40 volts minus 2 diode drops plus maybe a little more voltage to account for this. But the fact of the matter is that it would end up pretty close to VCC here, within I think she said, that it actually comes within like 1.8 volts or something. So, but I mean, that sounds about right. Of VCC max. But the point is that that's how this thing would behave in its quiescent state, assuming nothing else was happening in the circuit. So it wouldn't be a variable power supply, but it would actually turn on. So, because again, you don't need any of this stuff for the thing to turn on. You could literally cut all this circuitry out of it. including this, basically everything out of this. You know, I should have, well, here, I could do that. Let's see. Yeah, I could do this as a whiteboard.
Voltage drop across the resistor.
Alright. Alright, so yeah, I'll do it on this thing instead so I can use it as a whiteboard. Although you can't see my cursor as good on this, that's why I kind of hate this thing. I don't think I can get a wider one. You can kind of see this. Okay. But, well, shit, the undo key doesn't work. God damn it. Shit. That sucks. Anyway, but the point is that, you know, you could probably... I mean, what idiot does not put a fucking undo key on a drawing program? But at any rate, you know, you could get away, you know, with that. Yep, fucking no undo key. I can't fucking believe this shit. I mean, is Microsoft just like purposely stupid? God, you know, this thing is annoying anyway, and now it's, I know it's useless. I mean, not even a single level undo. That's just unbelievable. But at any rate, I'm saying, you know, you could just ignore that and you know, and the circuit would still do something. So anyway, that's as far as I've gotten so far, so let me think about this some more. Anyway, what I'm doing right now is changed over to paint, by the way. But and how I started this whole thing is to assume that I've actually got this set to 20 volts, and the question I'm trying to work backwards to determine is, okay, well, where does that leave everything, you know, to get at 20 volts. Then we'll deal with current later. But that would put this at 21.4 volts right here. Again, this is still at 40 volts. So, you know, that means on average, you know, you're pulling, you know, like 200 microamps through this thing. So, and again, right now, since we're not considering any of the rest of the circuit, you know, that 200 microamps only has this direction to go. So, that gives you a basis for analysis that we can deduce that we may have, you know, because we will have, under all circumstances, you know, again, like what, 18.3 volts or 18.6 volts across this resistor. So I wonder if I can type. So I'll put that there. Alright, so, you know, if that's our voltage, I guess once you enter that you can't change it. But if that's our voltage drop across here, at least it is, you know, it's got to be, because there's no other choice, because we've got these. And the only difference is that it'll change a little bit depending on the current flowing through here, but right now we're assuming there's no real current just yet, although there could be. But we're assuming that there's none, because we're assuming we got this set, and this is this thing down here, you know, this is what you set the current with. This is what, I mean, that's what you set the voltage with, and this is what you set the permanent, you know, the upper limit of voltage with. So this is like a fixed potentiometer, whereas this is on the panel. and this is what you set the current with right here, and this is what you set the upper limit of the current with here. So again, this is on the circuit board, this is on the panel. But at any rate, the one thing we know is we do actually have, because this voltage is, you know, right now, it's for all intents and purposes, you know, it's rock solid. I mean, it's, you know, monolithic. Oops. Okay. Now the question is to figure out what does it take to make this voltage equal to 20 volts. What else is going to happen in this circuit to do that? So let me chew on that. Now I will say that one of the things she said is that this stuff here, along with this transistor, you know, that it's hooked to, is about the current control. So again, right now we're not considering current, we're only considering voltage. So we'll try to leave that, although this is part of the voltage circuit right here. You know, so like I said, this thing here is part of the voltage circuit, so we want to, you know, keep that in mind. Okay, and some other, you know, rather obvious things here. This, of course, is a differential amplifier of sorts. Okay, its output basically is here, coming off its collector like you'd expect. This input goes to our potentiometer, which is the primary method with which voltage is set. This is a 10 volt Zener, this is a 2 volt Zener. So together these make a 12 volt power supply. With the 12 volt going to this is just a resistor, a 2.2K resistor that regulates it to like 20 milliamps or something like that. You know, it's 40 volts divided by 2,000, you know, so yeah, that'd be like a little under 20 milliamps. But this capacitor here is, you know, like 10 microfarads. It's pretty large. That's probably to stabilize it, and it probably helps, maybe help a little. Well, I don't know if it helped. I was gonna say it might help a little bit with how, you know, pots can be sometimes, you know, where they tend to skip. You know, it's like they bounce as you turn them. So, you know, I was thinking the capacitor across that might actually not be a bad idea, you know, to help you get over a bouncy pot. You got to understand something. I mean, I'm a digital / microprocessor designer, so I'm still trying to learn to think like an analog designer. So that's why I'm going through these this stuff this way. But let's see. But anyway, this potentiometer is a voltage divider, so you can look at this as 10 volts, and this wiper on this is going to be somewhere between 0 and 10 volts as an input to our amplifier, or rather an output, since this is a PNP transistor. So current will flow from this point through this 3.3K resistor through that base and to ground. Okay. So I would imagine this is actually acting like a PNP equivalent of a voltage follower. So that's harder to ascertain. You know, that's more or less what this is. But still thinking of it from a PNP sense still confuses me a little bit. But well, yeah, that should be a voltage, basically a voltage follower. So in theory, whatever voltage we set here is going to try to show up here, if I'm not mistaken. And remember, this, you know, is dropping 0.7 volts, right? So this is going to be, you know, 0.7 volts lower than this point here. And then this point, you know, is going to drop the difference. So you can take this 2.4 volts and subtract basically 0.7 7 volts from it, you know, so it leaves you with, like, you know, whatever's left over from that. So, you know, 2.8 volts or whatever, or I mean 1.8 volts or whatever, that may be across this resistor if this thing was turned all the way up. So in other words, if you had 10 volts here, that's the maximum it can go, you know, then that would be, you know, 10 volts plus 0.7 volts, so it would be 10.7 plus this dropping the difference on this 2.4 volt diode. So, but basically, you know, this would still be at, you know, at that 12-ish volts, you know, 12.4 volts. But in any event, that's if this is a voltage follower, okay, that's what I'm trying to say, you know, well, that's going to put 10 volts plus 0.7 volts here. So, you know, that put this at 10.7 volts. You know, because that's the voltage it's trying to impress across this resistor, again, ignoring this thing over here for right now. There's only one level. Well, I guess there's two. Good. So yeah, if you had 10 volts here, you know, again, ignore this. You know, basically you're going to see, you know, 10.7 volts here. If you had 0 volts here, you'd have 0.7 volts here, and a good clear-cut, you know, current path, you know, from this 12 volts down through to ground. So, you know, that'd be eating a lot of that current through that resistor there. But at any rate, the point is that it's going to put some voltage, you know, across this thing and try to supply current that makes that happen. Because again, you know, this is just a reference voltage that's coming here, but any current flowing through here is going to be multiplied by beta, so it allows more current to flow through here by like 100 times. So, you know, so whatever current that is, you know, this is going to be probably 100 times more flowing through the body of the transistor, trying to maintain this at the voltage this is setting it at. So, you know, plus 0.7 volts. So, now, of course, whatever current that ends up being, okay, is going to change the voltage across this transistor because it's in conflict with this resistor here, which gives us a, you know, there's only so much current that can flow through here in saturation. You're talking, you know, basically 10K plus 3.3K plus, well, let's just deal with that for starters, even though there's probably less than this. Let's say 12 volts divided by, you know, 13.3K. Well, I should say 12.4, but anyway, you know, it'd be roughly, you know, 900 microamps. So, you know, just looking at it from this voltage here and assuming it's fairly well regulated, so 900 microamps wouldn't tax what we got going on through this resistor here very much, given the fact, like I said, it's about 20 milliamps or so is flowing through the whole circuit, so that's a small fraction of it, you know, less than a milliamp. That's our saturation, you know, that's if this were turned completely on. Now normally it'll be less than that because that's the maximum current that can flow through that. You know, and of course at that level this is dropping, you know, a large fraction of the voltage, you know, of this 12 volts, for example. I mean, this is going to be, you know, like 8 or 9 volts or so, you know, based on that current. But again, in practice it'll be less than that, you know, but that's if we had it, you know, fully saturated. So, which the way to fully saturate it is to turn it down to 0. So if you turn it down to 0, okay, that's when you get most of the current flowing through here, and you're going to get the biggest, since it's honestly it's trying to multiply the most current by the most, because I said it's 900 microamps, so that'd be like 90 milliamps it's trying to allow to flow through here. So, well, no, I said 900 microamps would be flowing through here actually. So this would be a small fraction of that then, going through the base. So yeah, I mean, it's very, very little amounts of current. That's what we're really dealing with here. So, but still, that's going to drop a voltage, proportional to that, because this voltage is going to be high when this current's maximized. Okay, but that takes place when this is minimized, because that's, when this is basically 0 ohms, that's when you're going to have maximum current flowing through there. In fact, we can kind of figure, say, about 11 volts divided by 3,300 ohms, so that's going to have like 3 milliamps potentially flowing from here through this. It's actually potentially more current than will flow through here because this 10K resistor limits it, whereas it doesn't limit it here. So there's actually going to be more current flowing through the base of this thing that's flowing through the collector, interestingly enough. So in other words, this is definitely going to be saturated. That's what you get in saturation. Basically, you got more current flowing through the base than you do through the collector. That's an indication of saturation right there. But it's not always more current flowing through the base than is flowing through the collector. But in this case, it's an indication that this damn thing is saturated as hell. So I mean, it's really, really, really mega saturated, extremely saturated. So, when this is set to 0, so again, that's going to be at maximum voltage at that point. Again, like 10 volts or something, a little less than 10 volts probably, but right around 10 volts. So, and that's when this is set at 0. Okay, I don't know what 0 means. So, but it's the point we have 10 volts across this. So you can deduce that if I had 0 volts across this, or if I had this turned up to maximum resistance, you're going to have minimal current flowing through here. Not 0 though, because it's only a 10K resistor, and this is a 10K resistor. It's a 10K pot. So, you're really dealing with similar amounts of current, meaning that if this is turned all the way up, well, it's kind of in the sort of the same boat this is in, but just with a little difference that I mean, you'll have this 0.7 volt drop here, but potentially a smaller drop across here. Now remember, this transistor doesn't have to drop the same voltage, that is dropped through the base, because that's why this is 0.7 volts above this. But this might be at about that same voltage down here, if that's saturated. Anyway, it's got that potential. But yeah, if this is turned all the way up, that'll minimize the amount of current. Again, you'll be talking, instead of that 3 milliamps going through it, well, it'll be more like 0.9 milliamps. So it's the same as this, more or less. So so again, that's way smaller, but still, shit, you think about it, it seems like that'd still be enough to saturate the damn thing. But you will end up with 10 volts here, okay, and that will end up with and that's something I basically forgot to look at. Basically, yeah, if we did have this turned down to 0, again, it being the voltage follower that it is, this actually would only be at 0.7 volts right here. So this would be dropping the bulk of the voltage, So again, you would have that 3 milliamps or whatnot, you know, yeah, about 3.5 milliamps flowing through it. So, but that would be dropping almost this entire 12 volts, about 11 volts or so. So in other words, since this is dropping 11 volts or so, this would be actually zero, or damn near it, because, you know, this is dropping almost all the voltage. This is the voltage it's trying to follow, not this. So, you know, but basically almost all the current will be going through this, because it's actually trying to pull itself down to zero. So, you know, it's trying, even though it's got the most current flowing through it, it's going to see almost all that's going through the base. So, again, since it's trying to act like a voltage follower, it by its very nature has to be, you know, choking off current down through this circuit. So in other words, this should actually be at 0 volts or damn close to it, because this transistor should actually be, even though you got maximum current flowing through it, that's still going to be a very low voltage across it. This is going to be a very high voltage across this, and this is going to be turned off. Again, I don't, you know, I'm kind of confused about how this would behave exactly, because again, if you got maximum current flowing through the base, that's when you should have maximum amplification, right? But what that means is it's maximally saturated. So, but again, you got all this current being dropped across this, okay, and this 0.7 volts dropped across this point here. So with 3 milliamps flowing through it, even though it might be trying to allow a shitload of current to flow through here because it'll be a low impedance path, this is still going to be a higher, or this is pegged to ground, because this is set to 0, right? So since it's at ground potential, well, this can't be any, you know, again, since we're talking PNP transistors, this can't be any lower than that. So basically it crashes its base into the ground. That should have the effect of turning the transistor off, because it's crashing itself into the ground. So I don't know if that's true or not, because again, I'm just not, you know, still trying to figure all this shit out, really. But if that's true, then this output will be basically 0. Like I said, you put this at 10 volts. Okay, well, that's going to put that at, you know, 10.7 volts, but it'll be minimal current flowing through the transistor, because it's only got 2.4 volts above this setting here, you know, to work within, minus the voltage drop across this diode here. So, you know, about 1.7 volts is what it would work out to. So, you know, if it's got just 1.7 volts across it, and then basically 10K to flow through, well, that means you got 1.7 volts essentially across this 3.3 ohm resistor here. So you're talking 1.7 divided by 3300 ohms. So you know, it's going to be like, you know, 500 microamps or so. But still, that could be like upwards of 50 milliamps, you know, the transistor is trying to allow, you know. But of course, the transistor won't be able to supply no 50 milliamps, because that whole circuit can't supply that. So, and certainly it's not going to be able to supply it through a 10K, you know, or 10K potentiometer, plus this 3K resistor, plus this 2.2K resistor here. Even though it's got 40 volts across the whole thing, it's still not going to be able to supply, you know, that much. In fact, let's add that up. So 3.5, so it's 15.5K, 40 volts divided by 15,500. So again, it's really about, well, really, it's worse than I thought. It's only 2 milliamps, 2.5 milliamps. That's the maximum that can flow through this circuit right here. You know, would be 2.5 milliamps. So, although, you know, you can still have current flowing through here, you know, through these diodes, so there's a potential for more current to flow through that. I mean, it's really actually 40 volts minus 12.4 volts divided by 2200. So, you know, it's about 12 milliamps, you know, would be about what you would expect at maximum to flow through here. So again, this is going to be getting a fraction of that 12 milliamps. But again, it really can't supply that much current. So the point is, though, is that, you know, since this is above ground, there's still current enough flowing through here to activate the transistor. You know, so, you know, if you got the transistor, you know, some current flowing through it, well, there's also going to be current flowing through the collector of 100 times that, or at least trying to. Okay, because again, what we calculated it could be going through the base could also just as easily divert over to here. In fact, you've got two resistors that are essentially in parallel, so it's 5K of impedance plus 3.3K, and that'll give you what the overall current flowing through this 3.3K resistor is. So, more or less. So it's 12 divided by 8800 ohms. So it's about 1.3 milliamps. Now 1.3 milliamps divided by 2, or well, let's do this, times 3300, okay, implies about a 4.5 volt drop across this. So at any rate, yeah, about a 4.5 volt drop across this. So really, this is like 8-ish volts plus whatever this transistor may or may not be dropping, plus whatever we have here, which could be up to about half. And I gotta assume it's gonna be maybe equally split, because again, the transistor is certainly going to want to allow current to flow through this branch. It doesn't need as much to flow through that branch. So again, you still think it would predominantly go through here, but yeah, I'm just really not sure about that. That I'm going to have to think about. So, but still, the voltage going through those two resistors should be the difference. So, you know, it should be like roughly 8-ish volts, you know, across, you know, both of these, assuming the current were equal. But again, it probably isn't. There's probably 10 times as much current going through this branch as is going through this branch, which means that these really aren't acting like parallel resistors. So, but it still makes it hard to figure. Okay, well, if it's going to amplify current, well, how much current is being amplified? Because the resistors are exactly the same. And it's got the same impedance no matter which way it goes, because we got the knob cranked all the way up. So, I don't know. I'm still going to have to chew on this some more. Now, another observation I can make before I go any further, though, that's kind of interesting, is that this is an NPN transistor that's coming off of that with no resistor in between. So this is a 0.7 volt drop above ground. So that is always going to hold this at 0.7 volts, pretty much. I mean, it's not going to be able to get much more than that. So before, like when I said, you take this down to 0, and it'll crash it into the ground. Well, it probably could. I mean, it could possibly turn that transistor off, you know, if you actually crashed it into the ground, you know, with this being 0 resistance. That's not out of the question, given the fact this would have to be 0.7 volts above ground. And if that were 0.7 volts above ground, okay, well, that means this has to be a lower voltage, because it's on the collector, than what the emitter is. So it's going to be at least 0.2 volts or so lower than that. Okay, so that's going to put it below the conducting threshold of this transistor. You know, if you did crash it into the ground, and it wouldn't be able to, this transistor would be turned off over here. So, I mean, that would be like gone if you turn that knob down to nothing. So, the question is, so if you turn that knob down to nothing, again, this is virtually zero. It's really close to zero. And again, this is what's connected to this little thing here, which is supposedly involved in the current. We're going to ignore that for the moment, but I do want to take kind of a brief look at it. Yeah, let's assume that doesn't do anything for the moment. Because again, you can have a power supply without current adjustment, right? So let's ignore that. But in realizing that extreme case, you know, taking this down to zero, yes, that turns this transistor off. Okay, if that transistor is off, it'll basically allow this capacitor to charge up. Remember, this is still like, okay, in our example, this is set at 20 volts, right? Because we're trying to assume this is 20 volts here. So basically, you know, yeah, this is going to be at 21.4 volts or whatever. So that's what this capacitor can charge up to, because this holds that pretty stiff to that voltage, because that's what the current works out to. Okay, we got some kind of a load going through this bulb, and you know, we got it set to 20 volts. So the question is what would this do if this were gone? You know, and you got a capacitor here. You know, is that just going to charge up to this voltage of 21 volts, or is it actually going to charge up to 40 volts and turn everything off? So I'm not sure, because again, before we were considering that none of this was hooked to ground, but now it kind of is going through this capacitor. The capacitor can actually build up a charge on it. So in addition to the charge on this, now at this point though, we may actually have to start considering these two resistors here, which one's variable and the other's fixed. 25K plus shit, I don't know what that is, 8K or something like that. So it's like 30 some odd K. So, you know, not going to be a whole hell of a lot of current. Probably about 6 milliamps or some shit. So again, this will actually have some current going through it. You know, 6 milliamps minimum or whatever, depending on how you set this pot. Maximum of, you know, whatever. Assuming that's, I almost don't like wasting time on it because I'm not even sure what the value of that resistor is. But, you know, let's say it's 2.4 milliamps if this was turned down to 0. Okay? And if this was set to 8K, it's a 24K pot, it would be 4.8 milliamps. So, but at any rate, I'm not quite sure what the effect of this is yet. So, but my question is that, okay, see, this circuit does not affect anything since we're not yet considering this. This actually is an independent thing that doesn't enter our equation because it's really just taking current from here and sticking it down to ground. But we have 20 volts across it, right? So it's got a load going through there that we can define. So that's drawing current through here, and a very small amount of it that's going off to our load, that should be a path to ground for this capacitor to discharge through. So again, I'm thinking it would still be, again, assuming this is actually regulated, this capacitor won't charge up to any more than 21.4 volts with this transistor cut off. But the thing about it is, if this transistor is cut off, well, that means this current can flow unimpeded through here. So again, like I said early on, I said if there was nothing else to control it, I mean, all this shit was gone, this would buoy up to where this was just, like 1.4 volts. In other words, this would be like, 38.6 volts. So with this off, that's the only thing that I could actually be pulling that down to siphon current away from that base to actually keep it lower than, than 40 volts on the output. So since we, are assuming that it's, we're assuming that it's, that this is set at 20 volts and therefore this is at 21.4, this has got to be set, to a level that allows it to maintain that. Remember that these aren't connected here or anything. So, if it's not doing that, it's not doing its job. So this has got to be maintained at 21.4 somehow. So this has got to have enough current flowing through it to maintain this at 21.4 volts. Now, it becomes a little bit complicated because in this equation, okay, we got all of our current coming through this resistor, right? All of it comes through our resistor and goes down through this transistor. Not all of it, but all of it comes through this resistor. But again, some of it goes this way, okay? In order to turn this transistor on. But again, probably a pretty small amount because it doesn't really necessarily need a lot, given the fact you got so much gain here. I mean, this is potentially a gain of like 10,000 just with these two alone, and probably 100,000 with this power transistor here. I mean, it probably doesn't need a whole hell of a lot. So, so because of that, you can assume that not very much of this current is flowing through it. But again, this is a 100K resistor, so, if this thing were fully turned on, okay, to put it in perspective, that would act like a short circuit. So, that would have about, 400 microamps flowing through it. So again, this doesn't have to be turned on much to actually, pull this down to effectively ground. Doesn't require much at all, because it would be siphoning all the current away from this base then, if it were doing that. I mean, that's basically flat out connecting this to ground, okay, which is at a lower potential by 1.4 volts because of these two diodes than anything that would go this direction. So it would fully cut it off if this were fully on. So we know if this is fully saturated, okay, our output's going to be 0 volts. If this is fully off, our output is going to be 40 volts. So it all depends on this transistor being either off or on. So, right now as it stands, since it's at 20 volts, which is like right in the middle-ish, it's got to be somewhere in between. So, and again, it's a little hard to figure where, because, you got these two extremes, where 0 current is flowing through this and all the current is flowing through this. and you can figure out what current that is because it's at 20 volts, right? But and then you got the other extreme where all the current's flowing through here. None of it's going through there. So, but again, you know, the maximum current that could theoretically be flown through here is going to be 40 minus 21.4 volts. So it's 18.6 volts divided by, you know, 100K ish. I'm ignoring that sense resistor still. So again, it's going to be, you know, like, you know, 186 microamps. So that would be, you know, where it's got to be. Okay, so if you got 186 microamps flowing through that, you know, and you know that's at 21 volts. Okay, what's that? How much does this transistor need to be on to do that? You know, because like I said, you know, it can be, you know, up to 400 microamps, so it's about halfway in between that extreme completely saturated point and 0 amps. So that's actually where you'd kind of expect it to be, you know, given the amount of current we have if this were like halfway on, in other words, halfway conductive. So, because we know it's maintaining this voltage here, in order to do that, you know, because it's got some amount of impedance going through here, which isn't entirely clear exactly what it would be, but it's going to be, you know, less than, you know, 186 microamps. But then you've got, but right now I'm just trying to ignore that because, again, maybe it has a load on it, maybe it doesn't, right? So, you know, I'm trying to ignore the load as much as I can right now. That's why I'm trying to not deal with current just yet. So I can kind of look at it from the standpoint of a multitude of different loads on it. But in any event, you should be able to adjust the output voltage, you know, with a very minimal load on it, you know, like a 100K resistor or something maybe. I don't know what the minimal load would be, but, you know, I'm sure this is one pathway some of that minimal load could take. Because that will certainly establish a minimal load on it. But at any rate, yeah, we got 186, you know, microamps going this way, and then ostensibly some going this way to keep it at 186 microamps, because that's the reason we have 20 volts on the output here, is because this only has 186 microamps flowing through it. And it's got to maintain that, you know, as long as 186 microamps is flowing through this, you know, it'll keep this at that 21.4 volts, and it'll keep this therefore at 20 volts. So regardless of what the load is, this still needs, you know, that amount of current flowing through it, in theory, to maintain that. Just because that's what the voltages kind of voltage drops work out to be. So, you know, because I do know there's going to be a 0.7 volt drop here, a 0.7 volt drop here. I know this is going to be 24 volts. Like I said, that's monolithic. So because of that, I can tell you how much current needs to flow through this resistor, which is just connected to here. And there's no other way, nothing else affects the voltage through this resistor except this channel here, and what current flows alternatively through this transistor. So it's this transistor and this transistor's voltage drops, and the voltage drop on the outside that actually affect the current flowing through there. And again, at first, you know, if the thing didn't have any control circuitry in it, this would be completely, you know, minimal, because this would be like 38.6 volts. So that's very little voltage to drop across it. So there'd be like minimal current flowing through this thing at that point. So, again, ostensibly less more current was being drawn, but again, we're not dealing with the current draw yet. Just looking at it from a voltage standpoint, yeah, if this were off, this would be at maximum current or maximum voltage, and that would be minimal current flowing through this channel, but there would be some current still flowing through that channel. because again, we do have at least some load going through this stack here. So, at any rate, the question is, like, okay, if this were 0 volts when we started up and first plug this in, and let's assume this thing's off, again, if this thing's off, the voltage, like I said, is going to rise and rise and rise with nothing stopping it. So, because again, this is off, except that it's going to charge up this capacitor here, because that's still acting like a short circuit when the thing's just turned on, so it's actually going to be sinking that current down to ground at first, okay, which is actually trying to keep that output voltage rather low, because again, if this had no current flowing through it at all, this thing would basically be 0 volts on the output, because all the current will be diverted around it and none will be flowing through the base. That means all these transistors are shut off. So yeah, I mean, in other words, it'll start out in an off condition just thanks to this capacitor here, and that's a pretty substantial capacitor, 4.7 microfarads. So, but again, this will charge up, so it makes it almost a soft start circuit a little bit. But it will charge up and raise to a level until something stops it. And again, we're saying it's going to stop at 20 volts. Okay, what would stop it at 20 volts? We know there's got to be 186 microamps of current flowing through this channel here, but how much current needs to flow through this to make that happen, I don't know. I mean, because you get some impedance here, okay, which is essentially in parallel with some impedance here, making a total current flow with the same voltage across both at 21.4 volts. Again, don't know what this impedance is, don't really necessarily know what this impedance is unless you want to just consider this and don't look at the adjustments at all, because I don't know if that would make a difference or not, though. That's the thing, I still don't know what actual effect this will have yet. So, so I really can't tell you exactly how that would divide out, except to say this has almost certainly got some current flowing through it, nothing else, to keep this capacitor from charging up to 100%, because otherwise it will. I mean, eventually, just through this resistor, it'll kind of charge this thing up to, this voltage minus this voltage drop here. So in other words, it would charge up to a pretty high voltage. But anyway, so anyway, I got to think about it some more. But I do know that the voltage setting is proportional in some way to the current flowing through this transistor. I don't know if it's linear, but I do know that some current between 0 and 100% of this, that whatever 186 microamps or whatever the maximum was, the 400 microamps. But if this had 400 microamps flowing through it, there's going to be 0 volts or 100% of the voltage, will be going out here, or no, um, I mean there'd be 0 volts on the output, but if it has no current flowing through it, um, you know, there'll be maximum voltage output. So I do know the voltage output on this power supply is a function of what's going through this transistor. So, and this transistor, its current is dependent on, our friend over here that we're messing with. So, again, now that we know the voltage is pretty much pegged, we know if we take that down to 0, that's going to bring this down to 0, which will crash this and turn this off. So we know 0 actually corresponds to 0 output, so we can deduce that 10 volts, in other words, turning it all the way up, corresponds to maximum output. So, well, actually, we know that turns this off, which if this is turned off, this will be maximum output. So we know 0 on the knob here actually corresponds to maximum voltage, whereas 100% or 10 volts should correspond to minimum voltage, which means that's got to be where this transistor is fully turned on, which makes sense, because at that point, most current is going to be diverted, through that transistor, because again, that's going straight to ground. It's got a 10K resistor there, which isn't going to offer any fuss. So basically, yeah, that current is going to be maximally flowing through here, whatever that means, if that were turned up to 10 volts. Because like I said, even though this is 10K and this is 10K, really there should be like 100 times as much current flowing through this as this. So there should be like a ratio like that. So if you have 1 microamp here, there should be 100 microamps flowing through here, and therefore through this transistor. So, like I said, I'm not exactly sure, where this needs to be, but I do know that if you look at it as a zero-sum game, which you can't do that, because again, there's going to be some impedance through this and some impedance through this. So you're not going to get ever a saturated current flow. So I just don't know how you look at it to work out how much current would actually have to flow through here in order for this to be at that 186 microamps. But there's going to have to be some amount of current. We just don't know what it is. It could be between 0 and 400 microamps, possibly. What limits it? I don't know. But I do know this helps set that, so it gives it a point to shoot for when this power supply is first turning on. So we got that knob set halfway in between, which should be, assuming it's linear, 20 volts, right? So that should correspond to, a 5-volt drop here-ish. Again, this is going to be pretty damn close right here. That'd be 5.7 volts. This will be like, 4.9 or something like that right here. So, or it would try to be, if you didn't have this on it, it would try to be. But as it is, no, you'll have that 5 volts actually trying to go through that. But, it's not going to actually have 5 volts across it, because it can't deliver that amount. It can't deliver 5 volts divided by 0.7. I mean, 5 volts. Shit, I don't even know what that'd be. That would be like an infinite short circuit, basically. So, in other words, it won't cook the base of the transistor because it's limited by its impedance. It can't do that, but you can kind of maybe sort of guess. Again, it's harder to say how much current will be going through here, and therefore how much current is going through here. But you can, I'd almost say, work your way backwards, but you can't. So, because again, you don't know. I mean, I just know how much current has to flow through, like, this resistor, because of the voltage here. So, The problem is if that's all you had flowing through it, you know, I know that, so, well, I do know that, like I said, you know, because of the voltage here, I do know how much current's flowing through this resistor. Because of that, I do know that out of that current, some of it's going to go this way, and some of it's got to go this way. And that depends on the impedance of this load. But I can deduce what the overall impedance must be, right? Since it's a 100K resistor, and it's, you know, 18.6 volts across it. You know, I can tell you it's got to be, you know, 186 microamps. It's got to be flowing through that. Now, at 186 microamps at 1.4 volts, that has to be about, motherfucker, it doesn't make sense. Okay, it's 21.4, hold on, divided by 0.000186. Okay. Alright, so it's got to be like, you know, 115K. So, in other words, this should have 115K of impedance, which includes what's going through this transistor and what's going through this load. Again, it's still hard for me to tell you what's what unless you start, you know, setting the value for the load, and I don't know what effect this has. So let's just say I had let's say we have, I don't know, 100K load or something like that. So that's like a minimal voltage drop going through this and everything else. So it's like 400, you know, microamps overall, you know, at 100K, you know, across 40 volts. So, you know, that's roughly what we're going to have, but we know we've got, you know, again, that 186 microamps. You know, of current basically flowing through this resistor. Hold on. Okay. So we got 186 microamps flowing through here, you know, but we know that we've got 115K of impedance total, but then we're going to assume 100K load here. So, you know, that's 100K, but, you know, that's in parallel with whatever we got going on here, because we know that our total resistance is like 100K, because it's got to be that no matter what. So if we had 100K load, which is a very light load, we know that that's in parallel with some other value of resistance, giving us, you know, 15K roughly. And again, I'm kind of ignoring the voltage drops here a little bit, so there's going to be some error in this. But, you know, again, it's a question of, you know, 186 microamps, you know, or in other words, 100K of impedance, you know, in series with, you know, 115K. So, you know, which is, you know, 21.4 volts. You know, with one of the resistors being in parallel. So hold on. Okay, so if this had a 100K load, remember this is going through the base of a transistor, so you got to reflect it through that. So assuming the beta is 100, it'll be 100 times the 100K, or in other words 10 mega ohms. So you're talking like 2 microamps or something. So again, most of this 186 microamps is going to be going through this transistor. Almost all of it. So, you can pretty much consider, it's 184 microamps going this way, and 2 microamps going this way. So that's how much this has to have. It has to be, something of that neck of the, nature. So if that's got 182 microamps flowing through it, and this is a beta of 100, well, this has got to have about 1.8 microamps going into the base of this. Although this is significant error, but it's for shits and giggles. So if that's got 1.8 microamps going through it, okay, man, that's like not much. That doesn't require much at all. And we know this has got to be set, presumably at, like 5 volts, halfway in between. So we got 5 volts, and we got whatever it takes to have 1.8 microamps flow through this load, because this is still way lower of a load than this thing is. So basically you can kind of assume that there's 1.8 microamps basically flowing through this thing. So how much needs to go through this base? Shit, nothing at all, right? So where does this kind of come from? All right, that becomes the question. Well, I guess if so much current's going through there, well, some of it's got to be going over here. I don't know. So, but sure doesn't need much. But again, remember, there's nothing impeding current from going from here through here, because this is just like a diode. I mean, as much, I could put, 100 volts through this thing and have 100 amps flow through it. So, nothing really limits that. But how much current flows through the collector as a result of that remains to be seen. But again, this is a pretty large amount. So, but there's got to be some kind of action that takes place to get these values as low as they apparently have to be. So assuming that I'm right, that this needs to be at 5.7 volts, then this other needs to be at 5.7 volts on this other transistor over here. And that's dropping the full 5.7 volts because there's no resistor on its collector. So, but it's getting its reference from over here, so this has got to be 5 volts too. So, if that's the case, we know that this is, like I said again, I guess 8.2K. Let me try to make sure of that. Yeah, it's 8.2K. So, if you have 5 volts with 8.2K, you got to have a current of about 609 microamps flowing through this resistor to get 5 volts here. Now, not all that has to come from this 20 volts up here, though. Some of it certainly could flow through here, because again, it's got, it can easily supply that. Assuming none were, though, it would be, let's see where this comes out of curiosity, 609 microamps times well, no, not times, because I don't know what the resistance is, but say it's 20 volts divided by our answer here. So this says it would be set to 32K, but it's only a 25K resistor. So, you know, it's not 32.8K. So this could be turned completely off in theory, I guess, and because this is supposed to set the upper limit, so this could actually be set to 0. If it were set to 0, this would mean that you got 20 volts across here going down here, and then 20 volts going right there, which is probably going to confuse the shit out of this thing, since this can't go up to no 20 volts. So I don't know what that would do. I can tell you that no current would flow. Well, I mean, you might have current that flows here, because remember, this is still 12 volts here, but it's still coming from a 40 volt supply. I mean, you know, I don't know, you know, you might be able to get something, you know, but still, that would still be having to flow uphill because of this Zener diode here. So really, you wouldn't see anything flow through that from this angle, so it would have to be just flowing from here. So in other words, it's a big no-no to set this resistor to 0, basically, I guess. Because if you did, it's got to force this to be down within that range, because it's a differential amplifier. So we couldn't see 20 volts across it. If you did, I mean, theoretically, it would be set to 5 volts, because it's got to force this to 5 volts somehow. You know, whatever it's going to do, it's going to adjust this output to make this come out to be 5 volts at this point. So, you know, if you had a big ass resistor here, you know, like 25K for example, well, okay, it's 25K versus 8K, that puts it on the low side. So, you know, it's like what, you know, 33K total. So, you know, that 33K, you know, how much is 8,000 of that? God damn it. Okay, it's about 24%. So, if I really want to know, so about 24% of that is, you know, 5 volts. We got 5 volts drop. You know, across our 8.2K resistor. Okay, that puts it, you know, 20 volts. So as long as this resistor is turned fully up, it will, again, based on the current calculations we made, it'll come out to be like 20 volts, based on this theory. Okay, that this is set to 5 volts, this is going to be set to 5 volts, and it's set to 5 volts, that's halfway in between, so it works out to be about 20 volts. Now if this were 10 volts, you know, you'd have this point being at 10 volts, that being 25% of the voltage drop across this chain, and therefore this would be at 40 volts. Okay, so that's where this comes from. Now of course, if I reduce this to 0, well then 5 volts would be where we would be at 5 volts, and 10 volts is where we would be at if I set this to 10 volts, and 10 volts would be the maximum limit. It couldn't be bigger than that, because this thing is going to adjust. This differential amplifier will send enough current through here to make sure that this voltage and this voltage are equal. So if I'm understanding this correct, because I know this voltage is going to be equal at the base, so given the fact this has a constant voltage drop across it of 0.7 volts, how could they not be equal voltage? So the voltage here has to be equal to the voltage there, you know, for this type of amplifier to work. These two have to be equal. So because of that, if we have this set to 5 volts, that would have to be at 5 volts. Now, if this were set to 0 ohms, you know, now the equation, well, then 5 volts would be the output. So that does set the ceiling in the sense that it's a voltage divider. So right now this 8K resistor is about 1/4 the total resistance of this chain, and because of that, that's why it's getting, you know, a 1 to 4 ratio. So it's looking at 1/4 of the voltage here. So in other words, this goes to 10 volts, this can be at 40 because this will be at 10 volts. So that's what's going on basically, is that, you know, these two have to be equal. So this is the feedback. Basically it's taking a sample from our output and saying, hey, is this greater than or less than the voltage at this output input. So let's assume it was 25 volts. Well, okay, that means 25 volts, that's bigger, so that means less current is going to flow through here, right? So if less current flows through this transistor, I mean, basically that would shut it off. Because again, we know that this voltage here has to be 0.7 volts above this voltage here. So if this voltage becomes bigger, that's going to shut this transistor off, basically. And therefore any current that was flowing through it now has to all flow through this deal, right? Okay, now since it's all flowing through this transistor, well, you know, it's got this base here with no resistance on it. It's waiting to receive anything you throw at it. So it'll eat all that, okay, and turn on more, okay, which will divert more current away from this chain here down through here. And in so doing, it'll decrease the bias going through here and therefore decrease the current flowing through here, which decreases the voltage, right? So less current flowing through it, the voltage should fall. So because basically our impedance is increasing on this transistor, it's turning more and more off. And like I said, if it was completely off, this would be 0 volts. So but anyway, it'll keep turning off until, you know, that drops that extra 5 volts down to 20, you know, down to 5 volts here, okay, which means the output voltage, instead of being 25 volts, will be back down to 20 again. Now if it dropped down to 15 volt because our load, you know, really increased all of a sudden, then basically you see more current flowing through this transistor, and because more current's flowing through it, you know, because this voltage has fallen off so much, basically that siphons current away from this transistor, so you got less current flowing through here, okay, which means less current flowing through here, which means less current going through here, which means this turns itself more and more off. So as it turns itself more and more off, the voltage, you know, tends to rise here, because now more current can actually go through this direction. Okay, so that has the effect of increasing the voltage, so that it right up until it makes up for that difference, you know, that 5 volt drop. So that tends to, this differential amplifier action here tends to bring it back into equilibrium. So okay, but at any rate, you know, so that's basically what's going on with the differential amplifier. But it really is about how these things share current, and the fact that the voltage of these bases, these emitters, has to be the same, and because this voltage is fixed by our voltage divider here. Again, I could put a battery out here, and get the exact same results, because that's a hard, stiff supply. You're not going to overcome it like a car battery. Okay, I can put a car battery as a voltage divider based on that, or just a car battery, one of those 6-volt lantern batteries. Okay, if I did that, it'll be 6.7 volts there, but this by default has to be 6 volts too, because that voltage drop has to be maintained. If it's not, it's going to affect the current. Either more current's going to flow through here, or less current's going to flow through here, which means more current. This is going to be more on or more off, depending on how much current flows through this thing. So basically, I guess that light's burnt out, the one above the garage, because I was thinking it might be because of the temperature, but now the temperature's back. It's like 42 degrees out there, for crying out loud. Snow's half melted, damn it. Hell, it's probably going to be gone by tomorrow. Sucks. I guess I can show you. So that's the snow as it currently stands, but you can see the lights still burn out there. But it's all infrared now because it's the dark. But and you can still see we got some snow, out there still. But it's definitely falling off. But yeah, that's how those differential amplifiers work. So it's just a matter of, give a little here, take a little there, and that's what kind of, determines what it's doing. So alright, well, this is still in infrared mode. See, shit, man, there's just not much snow out there. Man, that sucks. It's nice having snow. I love snow. All that snow I'll ever see. Like I said, we still got some snow out there right now. Not for long at these temperatures. It's like, almost 10 o'clock at night. It's still 42 degrees out there. Anyway, but yeah, so that's how these differential amplifiers work. It's really just a question of fact. These voltages have to be equal, and because you got the emitters tied where they're at, that means these voltages have to be equal. And the better match the two transistors are, the more true that'll be. But that's what basically has to happen. And so if I had like a battery here, again, that would maintain a stiff like 6 volts. For example, therefore 6.7 volts, that would mean that this has to be 0.7 volts here too. Okay, but again, the battery is just an impedance, basically. That's still not the source of current through that. The source of current's coming through up here is some other power source. And again, this could be actually attached to, like, right here. We could attach it to 40 volts and just bypass all this crap and supply this with a battery. Okay, then we got 40 volts divided by 3.3K. Well, the current flowing through this is going to be dependent on how much current is flowing through both of these transistors. Now, how much these transistors need to be turned on, you'd figure, I think they would be about equivalent. In other words, this base current here this base emitter current here would probably have to be equivalent to this base emitter current here. But again, that would assume they had equal impedances, and they don't. So, because ultimately that's still going to affect how much current flows through this chain here. This has got a 10K resistor on it, this has got a 0K resistor on it. So there's way less impedance here to load this transistor. So any voltage it's got here, if these voltages are going to be equivalent, this transistor will be, again, I said, 6.7 volts, right? So it's got 6.7 volts down to 0, but it does have a resistor here to take up some of that voltage. Okay, again, if you exclude this, then basically we know this is going to drop 6.7 volts, transistor plus resistor, and we know there's going to be a current because we've got like 40 volts flowing through, right? So some of that current's got to go through there, but it's got to be enough to maintain this at 6.7 volts because it's a voltage follower, upside down, but a voltage follower nonetheless. That's why really these are easier to look at. If you use NPN transistors, they're a little easier to understand. But because this is like upside down version of that. But that current has to flow into it. Because the NPN transistors, you'd be looking at current from the battery, instead of flowing into the battery. But at any rate, the point is that this transistor here actually has a resistor to share its load with, so it won't drop the whole voltage of the battery. Whereas this one over here, it doesn't have a load, so it's got to itself drop 6.7 volts. So this transistor is going to be conducting differently than this one, because this has got to drop a voltage across it, but it's got no voltage, so it has to act like this resistance plus this 10K. It has to mimic that. So to get that same voltage to flow across it, it's got to have the same impedance that this has. So it's got to be 10K plus whatever, wherever this works out to be. But I think you can kind of assume that the current flowing through here, though, is probably mostly going into the load, whereas here, again, the transistor's having to mimic the load. So like I said, it's going to have a different, again, I don't know for sure if it's going to have a different current, but if these were exactly identical transistors, the voltage drop across these diodes would have to be as a result of an identical current flowing through it, you would think. But still, how much amplification is taking place, in other words, how much of this current is diverted down here, again, because this has got to mimic that, so the same current should be flowing through here, basically, that's flowing through here, but this is going to have a different voltage across it than this, because this has a load, a rather substantial resistor on it, and this has none. So it's really just a question of it adjusting itself, again, to where, at the case we were working on, where it's at 5 volts or 5.7 volts here. So it's got to have enough current to, flowing through here to maintain that, which really, is kind of going through this thing, because that's just a distraction, sort of. So because this is 0.7 volts, therefore that has to drop 5 volts across it, right? Because this is at 5.7 volts, and this is at 5 volts, so this is going to be just a little below 5 volts, but it's going to drop only 4.3 volts. Because you subtract this diode drop and just to basically ignore this, assuming it's an open circuit, okay, well that gives you, like I said, 4.3 volts this transistor has got to drop, whereas this transistor's got to drop the whole 5.7 volts across it. So again, there's still got to be something a little different going on in this transistor than this transistor to make that happen, but the impedances should match overall. This has just got to have a higher resistance than this transistor because it's got a higher voltage it's got to try to make up for. Again, now if we assume this wasn't in the circuit, then, because that's probably okay, I guess, except that it wouldn't have a means of controlling anything, but still the relationship would have to try to, I mean, even if we didn't have any means of feedback control, okay, it wouldn't matter. These two voltages have to be equal, and these two voltages have to be equal because it's a diode voltage drop. So because of that, it doesn't matter if there's any feedback or not. These have to be that way, and that's what I was going to get to before, is that, okay, like we got 5 volts here. Now, if I put like a 10-volt battery here, okay, but this has got to be 5 volts and there's no feedback, well, that 10 volts, you know, is just going to, well, it would shut this thing off because of the flow on it. You know, basically no current would flow because it would try to flow backwards. You know, at some point that made that too big, it would exceed the transistor's reverse voltage limit on its emitter. But the point is that, yeah, no current would flow through this, okay? Or better yet, if I put like a 2-volt load here, a 2-volt battery, okay, well, a shitload of current would try to flow here because there's no resistance, so it would try to siphon all the current away from that, you know, trying to trying to get this up to that 0.7 volt drop. The problem is it's a low voltage, so it would have to drop it through the internal impedance of the battery, which actually could mean a quite high current would have to flow through it. So, and of course, if that happened, well, all hell would break loose. I mean, everything would kind of start shutting down. It wouldn't act like a differential amplifier anymore, I would imagine, just because, you know, it would act like such a short circuit. This might just draw it down too low. And it probably would too, because I mean, you know, you can basically ignore this. This has a high impedance, and, you know, 5K resistance, right? Because we've got it set halfway to 10 to 5 volts. Well, this has got like a 0K resistance, so yeah, it's going to draw all the current through that. None will go through here. This will end up being at a higher voltage, you know, way less than 5.7 volts. In fact, it'll end up being at 2.7 volts because that lower impedance will force this to be drawn down to it. So that means no current will flow through this. So, you know, you got a real differential amplifier deadlock. So that's what would happen if there were no feedback control and you put a very stiff voltage source on it, you know, low impedance source. So, but as it stands, you know, it does have a means of feeding back. So, and that's through this transistor. And since it's got this circuit, because, you know, you don't even have to have any of this crap. I mean, you could take all this shit out, and then they're just identical parts of the same circuit. You know, they look like a mirror image of each other, except that, like I said, if you put that battery on it, it would behave exactly like I said. It doesn't matter what the load is. You know, what matters is what voltage it tries to follow here. So, but again, you know, you put, you know, a really stiff low impedance source or load on it, well, you know, that's gonna, you know, draw it way the fuck down and really fuck this other side up. It's not gonna be able to follow it like it's supposed to, because it has no way of regulating itself because of that. But as it stands, it does have a way of providing feedback, you know, for this difference to be done something with. That's why it's called a differential amplifier, because whatever difference tends to flow through, tends to flow through here in an attempt to try to equalize itself. Goddamn fucking bugs. We're going to have bugs again soon. Those black widows I gotta do something about. But at any rate, yeah, I mean, because it's got this feedback mechanism, you know, that can, you know, go out here and cause more or less current to flow through this, you know, which causes our voltage to increase or decrease, which causes this voltage to increase or decrease until it matches and restores equilibrium. So, but that's in a nutshell kind of how it works as far as the voltage side goes. So now you got to think about the current side. Now, of course, an immediate observation is that this is at the same voltage as this, obviously. Okay, and this is still at our 21.4 volts. So that means we got 1.4 volts across it. So no matter where we put this can be looked at as a voltage divider, this tap right here. You know, and again, this is part of the adjustment, but it can be looked at as a voltage divider dividing up 1.4 volts, because this is always going to be 1.4 volts pretty much under all practical working situations anyway. You know, it's always going to be 1.4 volts, so this is always going to be a fraction of 1.4 volts you're trying to cram into this thing, okay? So because of that, okay. Okay, so that's at 24 volts, right? Now, what we're trying to achieve here is, you know, we're looking at this voltage here, okay? So this is really 1.4 volts plus this. So nominally, this is 1.4 volts when there's no current flowing through it. The more current flows through that, the more this voltage difference starts to increase. So, because again, that's part of the chain. I mean, you know, we got these 1.4 volts through these diodes here, but on top of whatever voltage is across here. So if that's like 0.5 ohms, like this is slated to be, and we had 5 amps flowing through it, that's going to be 2.5 volts. So now if it's 0.1 ohms and you had 5 amps flowing through it, it'd be 2.9 or 1.9 volts. So the point is, though, is this voltage will change by some amount depending on what this is. So the question is it really sort of maybe boils down to how big is this voltage drop versus this one? I don't know. Because again, this is still going to be at our 20 volts minus whatever drop is there. Yeah, but see, 20 volts is our ideal. It's actually right here. So this is going to be actually less than that. It's going to be less than that by this amount. Well, okay, so that means this is going to be 1.4 volts, just like I said before. But this may be less than 20 volts, so this may be less than 21.4 minus whatever voltage is dropped here. So, because like I said, you know, this has got to be at least 1.4 volts. It's got to, even if there's next to no current flowing through here at all, this has got to be dropping at least 1.4 volts at all times, right? So, but again, that begins to change, and it doesn't matter what you set. I mean, I could turn this down to 0 and this down to 0, okay, and you still have 10K in series here that's got to drop 1.4 volts plus whatever gets dropped here. So, in other words, you know, if these two voltages are unequal, you know, that's going to start changing the voltage input here, which starts to change whatever its set point is. So, but again, under normal conditions, the constant current source is going to be off. So what we know is this has got to be off. this cannot be siphoning current away from our voltage source, otherwise it'll affect the voltage. It'll tend to draw, through this chain, the this 21.4 volts down. It'll draw it down towards ground, the same as this transistor can draw it down towards ground. But it's even worse, because anything that flows through this transistor goes through this base of this transistor, causing it to turn on more, causing it to draw the voltage down more. Because remember what I said if this were saturated, it basically pulls this 21.4 volts down to ground, which basically pulls this down to, ground. So it crashes it into ground. There's no way it couldn't. So, I know this constant current source thing, needs to generally be off. This transistor does. But when something happens here to make these set points do something, because remember, we are dealing with a voltage divider here. Okay, and assuming this is 0 just for the moment, this is a 100K resistor, so this is 250K here, but this is the one you adjust to adjust the actual current setting. This is the one that's on the panel. So this is a significant amount of resistance, meaning, you're talking 11 to 1 ratio here. Only 1/11 of this voltage, which is 1.4 volts at least, is going to be across this resistor. The other 10/11ths are going to be across this resistor. So in other words, roughly, you're talking, 140 millivolts is across this, versus all the rest of it's going to be across this, in one way, shape, form, or another. Okay, and keep in mind, this is a PNP transistor, so current has to flow from here to here. Now, in order for that to happen, this voltage has to be higher than whatever the wiper potential of this voltage is. So the more the wiper is set towards this direction, okay, the closer it is to that direction, the closer its voltage would be to 21.4 volts, and therefore the bigger this resistance would be. In other words, if it were all the way over, it'd be at the full 100K. So maximum resistance. So, do with that what you will, but that's probably going to be the condition that tries to turn it off the most, right? Because, if we set it the other way, okay, then that's minimum resistance, and minimum resistance would be the most favorable for voltage to flow, because again, this point is at the same potential as this point. This point is 0.7 volts lower than this point. So whatever it's doing here has to be lower than that. So this is 1.4 volts right here. So 1.4 volts minus 0.7 volts is 0.7 volts. So if this is anything less than 0.7 volts, current will flow through this, and this will begin to turn on. So now, how would that happen? Is a good question. So how would that happen? Again, you got this thing over here you can adjust the range with. That has the effect of pushing all this resistance this way. So in other words, that tends to actually make it, it's like tilting a table, more towards the inclination of it to roll downhill, right? So, the bigger you make this resistor, the more it crunches this, because this is so much bigger than both of these combined. So it starts to push this more into the operational range. Because like I said, right here we're kind of dealing with not just this voltage, this 1.4 volts, which, like I said, depending on where this is set, if you set it past this 0.7 volt drop, voltage starts to conduct, because this is 1.4 volts. Even if there's no current to speak of flowing through this, and this is 20 volts, this is 1.4 volts, well, you go down to past that 0.7 volt drop, in other words, to where it's 20.7 volts, you go below that, current starts to flow through here, and our current limiter starts to kick in. It starts to lower the voltage by pulling that down, okay, which if it lowers the voltage, in theory it's lowering the current, okay, so because in theory if the voltage is, because again you can adjust the knob to where it does that and it'll crash the supply is what I think it would do, because it seems to me like that create a snowball effect. I mean, frankly, if I go and lower the voltage, well, that's going to lower the voltage here too, because again this ends up kicking in, so I mean, basically that ends up lowering this whole voltage platform. So I mean, it'll lower the voltage here, but it'll also lower the voltage here. So I mean, again, it may find an equilibrium, and usually it'll do that by decreasing the voltage here, because this, you lower this voltage, it tends to turn this crap more off, and turns this off. Okay, it's less current flowing through it, therefore less of a voltage drop here, usually offsetting the cause of this turning on to begin with. But you can accidentally turn it on with a knob. If you turn the knob too far this direction, it's going to cause this current setting to trip, and that's why you use this knob, I guess, to try to move it, that trip point one way or the other, I guess, although I'm not sure if that's the right side or not for it to be on, but the point is that it gives you something to kind of think about. So but yeah, anyway, so that's but that's kind of how it works. I mean, again, the greater the current, what you want is you want this voltage adjusted. Again, not so far this way that it causes the thing to immediately start tripping itself, but just shy of that, so that as the voltage starts to increase across here, that starts to lower the voltage here, okay, which starts to tilt it more the other way, so that this trip point kind of moves that direction, and once it runs into that set point, your trip point runs into your set point, well, guess what? That starts to turn this damn thing on. But other than that, you want this set to less than 0.7 volts below this. Because remember, this, whatever voltage is formed here has no bearing on this voltage here. Okay, because remember, this is flat out determined from these two drops. Our output voltage, on the other hand, is determined by not just that 1.4 volts, but whatever voltage is here too. So again, that'll start stretching this out. At some point, causing this voltage here to drop outside of what this once expected. So it's taken whatever span was here, okay, which, and again, in the the situation where we're at, I mean, I don't know where it would have been set, like 50K, let's say. Because remember, this is a voltage divider, right? So, but again, if the voltage we're dividing increases from 1.4 volts, you know, the larger the voltage, okay, the larger the voltage is where our thing was set. So let's say we had it set at 0.6 volts, which won't turn this transistor on. But now all of a sudden this increases, you know, from 1.4 volts, and let's say we had it set at the 0.6 volts. Now let's say we had it let's say we had it say we had it at 0.4 volts. All right. So, you know, the wiper was, you know, set to a point to where we had 0.4 volt drop here and 1 volt here, right? So for a total 1.4 volts. Now this goes up, you know, like half a volt, okay? You know, okay, now, you know, the whole thing's got 1.9 volts dropped on it, and you know, so it's a voltage divider, you know, at 1.4 volts, but now it's not 1.4 volts anymore. It's, you know, it's 1.9 volts, but our division point is still in the same place. I mean, you know, come up with simpler examples. But at any rate, it's like 28% is where we got the wiper set, okay, to drop that 0.4 volts. So now, but that's going to be 0.4 volts, because we're multiplying that times, you know, 1.4 volts. But if it went up to 1.9 volts, then that same quantity would be 0.54 volts, okay, which is not enough to turn that transistor on yet, but it's getting there, you know. In fact, at that level, you know, we know it has to be 0.7 volts, and it's 28%, so 1 minus 0.28, okay, you know, is 0.72, okay, damn it, prick. So anyway, it needs to be 3 times 0.7 volts, so 2.5 volts will be its trip point. So that's got to go up by, you know, basically, you know, like 1.1 volts to do that, okay, and give the fact it's 0.056. Goddamn piece of shit. Okay, that translates into, you know, a current of 1.96 amps. So in other words, there'd have to be 1.96 amps flowing through it for us to meet our theoretical trip point. So as long as it's below that, you know, we get less current than that, well, then it's going to be below that threshold, that turn-on threshold for this transistor, okay, and that keeps that close. But, you know, if it starts to hit that, well, it's going to start turning this on, which starts to diminish, you know, pull this voltage down, which starts to diminish the bias going through these gates, which is diminishing the current going through here, which is diminishing the fucking voltage going through the sense resistor. So, in other words, it'll find a balance point between voltage and current. And the more of a load we end up putting on it, you know, that drops it. Now, like, let's say we drop it down to 3 volts, okay, well, you know, if this were dropping 3 volts or whatever, well, it's going to try to adjust itself till it finds a balance point where it's not dropping 3 volts anymore. In fact, it'd be less than 2.4 volts, even if that meant that it had to lower the voltage down to 10 volts to keep this voltage to that 1.1 volt drop across that sense resistor. So that's kind of how it's taking place. Just to kind of give it a, you know, a cursory attempt at analysis here. So I mean, that's more or less what I think is kind of going on with it. It's a little squirrely, but you know, I do think that's probably a good explanation for it. And I'll save this. I guess I'll put this video in this folder too. Or at least a copy of it, depending on how big it is. Okay. Alright. That'll do it.